Our panelists are Lou Lommers from Framatome. We have Matt Richards from Ultrasafe Nuclear, Leo Eskin from StarCore, and Jeff Harper from X Energy. That's pretty good representation. So let's start with Lou, please.
Okay, thank you, Hans. Is everything working okay for you guys? I'm kind of loud, so maybe you don't even need it, but we'll see. And thanks for the opportunity to speak here. For this panel, we were kind of given a challenge. I don't remember your exact words, Hans, but basically, you know, how do we leverage our safety case, our safety characteristics to aid deployment? So I'll kind of talk about HTGR safety and how it relates to the challenges that we face in deployment. And first, I just want to give you, remind everyone why HTGR is a good thing, why it's an important thing. You know, it's a fantastic hobby, but why is it important? And really, you know, when I first got out of graduate school and went to General Atomics, you know, and at first it was nice to go to San Diego, but it's a little disappointing, really, because, you know, for these reactors are really pretty boring. They don't blow up, they don't melt down. It's really kind of boring for a young engineer, but over the years, as I've grown older and wiser, I've come to appreciate the benefits a little more, you know, and the safety case obviously is a key part of these reactors. Particularly, I mean, I work for Framatome and we sell large LWRs, and I think they're actually safe. You know, they spend a lot of money on safety systems to get that safety, but they're safe. But the safety of an HTGR is more fundamental. And it's important not just for safety's sake alone, but particularly for investment risk, because it opens up new market possibilities that we really don't have for large light water reactors. You know, if you talk to Dow Chemical, they are not going to take a light water reactor in their Freeport, Texas facility. That is clear. Okay, they are not going to do that because the risk to them and their facility is too much, and they're not willing to accept that risk. So that's having this walk-away safety, walk-back again safety, so there's no event in the design basis that you won't be able to restart the plant again afterwards. There's no chance of a plant write-off because of some accident, okay? And that extends to the adjacent facilities as well as your facility. So it's an important thing, and it opens up process heat markets. So HTGR is very important. All the discussion you read about and see on TV and so on, about solving the energy problem, most of that is focused on solving, really, I would say, the electricity problem, which is only 40% of the total energy market. The other 60% is virtually all fossil fuels. And so if you want to address that, you need something like an HTGR. So I could go on and on, but we'll move on. Now to talk more about the challenges that are faced to deploy this. You know, if it's so wonderful, why haven't we deployed it already? Well, the reason is because there's some big challenges we have to deal with. There are challenges for the first-of-a-kind plant. In terms of technology development, obviously there's a lot of technology that's required for an advanced reactor. For HTGRs, we're actually in a pretty good place. The key feasibility technology issues, I'll say fuel and things like that, we've made very good progress. We heard a lot about that this week on fuel, and we're making progress on graphite, even though we didn't talk about that this week. And so the major issues are nearing completion, I'd say. There's still more work to be done. There will undoubtedly, as we get into the details of design, there will be detailed issues that still require more R&D, but those are details of any design process that you would have to deal with. But the technology itself is pretty mature and pretty ready to go, so that's really not, even though we have more work that we have to finish doing, that's not the fundamental thing that's holding back first-of-a-kind plant. The fundamental thing that we have to deal with is the cost of design and licensing and demonstration. And to do all that, it takes 10, 12, maybe even 15 years, depending on how aggressively you pursue it. And it takes a lot of money, billions of dollars. Finis mentioned $1 billion for the design work this morning. Depends on the concept. Some concepts are simpler, some are more complex, but it's several hundreds of millions of dollars to do that. To build a demonstration plant, it's more $1 billion, okay? There's a lot of money there. And the problem of that is down below, when we look at the nth of a kind, okay, costs, we have challenges here too. We have to get the capital costs and the operating costs into a competitive range, okay? And we're certainly working on that, but I think that the reality is the market is not yet ready for this technology. So the market won't be ready for, say, 10 to 15 years anyway. Now, that's good because it'll take us 10 years to get there, but that means we have to get started now if we're going to meet the market in 10 to 15 years down here, okay? The problem is, as Finn has pointed out very well this morning, the payoff, if you're the investor putting up this billions of dollars here, the payoff comes decades later, okay? It's not something you're going to get, certainly not in the next quarter, the next year, the next 10 years. It's going to be 20, 30, 40 years later that you get that payoff. So that's a fundamental challenge, and we have to figure out what we can do about that. One thing I want to mention is the safety case. I wanted to tie this into safety, and so I think it's important to understand the history of the safety case of HGRs and how modular HGRs, I'll say, and how that came about. You know, in the 1980s, when I first was exposed to high-temperature gas-cooled reactors, we were working in large integrated plants, PCRVs, as we heard about on the THTR talk that Hans gave us at lunchtime. And so they're like 3,000, even 4,000 megawatt thermal plants. And they had very good safety characteristics, to be clear. They had a lot of the inherent characteristics that we leverage today. They had good characteristics. But at the end of the day, they still had to have some active safety systems for cooling and so on. And in the early 80s, it was recognized both in the US and in Germany that if we take those characteristics and we repackage the design, we could really leverage those things and we could come up to something. You know, we've always been careful to say, well, our reactor is not inherently safe, even though some people do say that, but we've tried to not say that specifically. But the bottom line is, at the end of the day, this is about as close as you will ever be able to come to an inherently safe reactor, okay? And the idea is that by going through this will give you truly passive safety. So I don't need power, I don't need operators, I don't even need the reactor cooling, okay? There's not much I need to make this work, okay, except the geometry of the reactor. Basically, it's the geometry of the reactor that gives me the characteristics that I have. I can eliminate a lot of safety systems, but there is a trade-off in terms of economy of scale. But the key thing is that the investment risk becomes very acceptable, and I can now take my design basis loss of cooling events and I can demonstrate those in a first-of-a-kind plant. I can actually demonstrate them. You can't do that with a large light water reactor, I'll tell you. I mean, you're not going to do that, okay? And so the idea is that this would, in the 80s at least, that this would lead to more public acceptance, and so we started going down this path, okay? But, you know, that doesn't come for free, okay? This passive safety capability doesn't come for free. There are benefits, as we said, of going to modular HGRs. You eliminate most of the active safety systems. You have incremental capacity addition, which is, I would say, a big plus of SMRs in general. We have very low investment risk, okay? That allows us, with the temperature range that we can deliver and the low investment risk, to surface process heat markets, which is an area that's not otherwise addressed. But at the end of the day, economy of scale still matters. And going from a 3,000 megawatt reactor to a 300 megawatt reactor, there's a hit that comes from that. There's no way to deny that, okay? And in the NGNP project, you can see that in these two curves here. Finis showed one of these curves this morning. Again, this is not a Framatome curve. This came out of the NGNP project. It was based on data that Ariba provided, also data that GA provided and Westinghouse PBMR provided. And then Idaho kind of massaged all the cost numbers to put things on a common basis and so on, and they came up with these curves. And Finis talked about this one this morning. The capital cost of the plant and the operating costs, the curves are similar. You see the trend that if you go to larger module sizes, you get lower costs. So by the same token, you can imagine if you went to 3,000 megawatt reactors, the cost would be even lower. I don't know where the curve would be down here, but it'd be somewhere lower, okay? One point of clarification I want to make, I wasn't my plan, but I think I made the print small enough you can't read this, but just in case you can read this, I want to just be clear, this curve here, it says this is the Ariba HEGR module, N-of-a-kind plant, 8 by 200, I think that says. So just to be clear, that is not the Framatome design, okay? that is a 200 megawatt pebble bed design. At the end, toward the end of the NGNP project, DOE was getting final packages put together for prismatic and pebble bed, and Westinghouse PBMR team was leading the pebble bed effort, but they ran into some problems, and so they asked Areva, because as Finis mentioned, we have a lot of historical reference with pebble bed designs also. They asked us to put that information together, and so that was the package that we put together for DOE at their request for the pebble bed design. But our reference design is actually the 625 megawatt steam cycle HGGR design that we have. And if it had been on this chart, it would be down here towards this end of the 600 megawatt line, because it's actually just a little over 600 megawatts. So just to be clear about that, I've had confusion with that in the past, so I want to be clear. Okay, so the question is, how do we address these challenges? And for the nth of a kind, I think that largely falls on the vendors to deal with that. We are certainly dealing with that within Framatome. By going to passive safety, you do get rid of some of the design and maintenance issues associated with some of the safety systems, okay? And that does lower capital costs or lowers design costs, so that's good. But most plants, I'd say vendors already have that factored into their design. There's fundamentally, you have to say within the limits of passive cooling, what can you do? And so in the early 80s, when we first went to these modular designs, the Germans, they went with pebble bed. In the US, we went with prismatic, but both designs ended up in the 200, 250 megawatt range, okay? But for the prismatic design, and within less than a year, so I don't remember the exact dates, but within less than a year, we had gone from the 250 megawatt cylindrical core to a 350 megawatt annular core. And then that design lasted for about, I'd say, about 7, 8 years. And then around 1990 timeframe, they went to the 450 megawatt design core. And then eventually to a 600 megawatt core when GA was looking at the GTMHR. And then we have gone to 625 megawatt. But that is pretty much the limit. With a passive safety and a prismatic block core, that's about as far as you can go. Okay, so we've, within the limits of passive cooling, we've done what we can in terms of economy of scale there. Okay, we still get all the benefits of the passive cooling. We maintain acceptable fuel temperatures for all the design basis accidents without active systems. Our best estimate numbers are actually down not 1600 C, they're more closer to 1400 C, but when you add in all the conservatisms, it's around 1600 C. Okay. There are other things that you can do in terms of simplifying and optimizing your design, and certainly within Framatome, we're looking at our concept now, and we have changes in mind that we're investigating that we can do. I'm not going to go into the details of that, but there are things that can be done, okay? Certainly, once you start building a fleet of these things, serial production may offer some benefits, but at the end of the day, I think we have to wait until gas prices have increased some, and or price of carbon increases, some combination of those two. So competitiveness we'll do the best job that we can, but being really competitive with the marketplace is probably not going to happen for 10 to 15 years. That's just the way it is. But we won't get through these first-of-a-kind design challenges before then anyway, I think. There are various things that we can do. Bottom line is, it costs a lot of money to design a reactor. It's not that just the few clever people that come up with the basic concept. That's important. But there's just a lot of drawings, a lot of analyses, a lot of reports, a lot of reviews that have to be done as part of the process. And there's a lot of work there, and that's why it takes a lot of money, okay? And the sooner, by the way, if you need to make a change in your design, obviously, you want to find that out before you've spent most of that money, not after you've spent most of that money. So a change in final design costs you an extra $200 million, maybe, whereas a change in conceptual design might only cost you, $1 million or something, depending on how far through conceptual design you are. So it's important. That's why the optimization things that we're doing within Framatome, we're doing early in the game. But all of this has to be done within the context of passive safety. There's one thing, licensing, there's a lot of talk about licensing, and we need to do this with licensing and that with licensing. And certainly licensing is closely tied to the passive safety characteristics of the reactor. I'm kind of a little bit of a skeptic in the sense that, to me, the fundamental, if you give me the money to design the reactor, I think eventually I will get it licensed. It's just a question of how much money and how much time it takes to do that, okay? And there are certainly things that can be done and to accelerate that process and streamline that process, okay? And the fundamental problem of licensing, though, is that it's beyond our control. It's something, if I need to change my steam generator material or my core configuration or something, I can do that. But as a reactor designer, I can't decide, well, this regulator is not working out for me, other than going to another country. But if I want to be within the US, I can't decide to get a different regulator. I don't have that option, okay? So looking at it from the point of regulation, then, certainly, safety has to be assured. There's no doubt about that, and that requires, independent oversight. I mean, the answer is not just to say the NRC should just go away, our reactor's safe, they should just leave us alone, we can do our business. It's not that simple, obviously. But, and to be clear, the NRC is working to address the licensing needs of non-LWR technologies in general, and of HCGRs in particular, I would say. And DOE is working with them. There are several different industry groups working with them. And Framatome certainly supports those efforts. We participate in those efforts. But at the end of the day, I'm just not sure whether that does enough. I'm not sure what words I want to use here, but the fundamental question is, can we really take advantage of the safety characteristics of an HCGR, okay? As we've said, this safety comes at a price, and if you make it difficult, if you don't give the developer credit for that safety benefit, then they're just going to go back to something else that they can do the design cheaper, develop, or a more competitive product that doesn't have those safety benefits, okay? So you got to give some credit for that. And I think the key point on this slide I want to make is that, in my opinion, and I don't know, Jim, you may have different opinions about all this, but in my opinion, the large safety margins that we have, they really call out for something addressing that in the process itself. It's not just a question of the margins that we're going to end up with at the end of the day and how much we actually, are better than the requirements. It's the fundamental process, I think, could benefit from taking into account some credit for the fundamental safety characteristics. So, in other words, if we just do the same basic process, we turn in all the same reports, we do all the same analyses, and the only difference is that we've used different material properties and different correlations in our analyses, but we haven't bought ourselves much of anything then. And at the end of the day, we get better answers, but as a developer, it doesn't help me get my product to market, really. Okay, so I think, and these are just some thoughts, more brainstorming than anything else, but in terms of what could be done or what types of things could be considered, and I think some of these things are already being considered and discussed, or things suggesting similar to these ideas, but still, I would just want to mention these. I think there are some ways to focus the review process in light of these benefits and our characteristics. One thing is to look at alternate review strategies for methodologies, okay? Do we really need to review methodologies in the same way that we do for a large light water reactor? We know that the phenomenology is different and so on, but in terms of the fundamental amount of margin in that review process, whether that needs to be the same or not, I think that's a fair question, okay? The required level of redundancy and diversity in the safety systems that we do have, is that, if we're relying on inherent characteristics of the system, which have been assessed and are known, then do we really need the same level of diversity that we would for engineered systems, okay? Let me see where I'm at here. What the required level of uncertainty is that we have to satisfy. How precise do our correlations have to be when we have very large margins? I think that's a fair question. I think we want to be careful to focus. Excuse me. We want to focus the reviews on the things that are of true safety significance, not, sometimes the reviews that I've been involved in, not so much for HEGRs, but for other things, it can seem, at least, to the person on the other side of the table, like the reviewers are just kind of the review process is following the whims of the reviewer more than what's really fundamentally important to the outcome at the end of the day. I think everybody has to be disciplined in that regard, okay? And you know, going back to what Jim said, Jim Kendall said in his presentation or comments earlier, I think we need to keep in mind that a lot of these things, we will demonstrate these things in the first-of-a-kind plant. You know, this is not something that we're signing away the paper, the safety of the public on something that we never will know whether these calculations, how accurate they really were. You know, we will do these things, okay? We'll do them carefully under controlled circumstances, but we will do them. I think we have to avoid the temptation. This is certainly not NRC policy to do these things, and it's not intentional, but it's to some extent just human nature, I think, you know, to kind of find, well, where do I have to go? I'm trying to make sure that nothing bad happens. How far do I go before something bad happens? Well, one approach that you see sometimes is, let me find something bad that happens and then see how do I prevent that. And you want to be careful that you don't go to non-credible links to do that, I think, okay, no matter how improbable the events are. The other is you don't want to impose a relative safety standard, which is to say that the safer your concept is, I'm going to hold you to a tighter standard than I would maybe hold the other guy to, you know. Or you also see that in however safer you are today, I'm going to put a few more requirements just to make you a little safer, and then I've done my job. Again, these aren't things that I think are active policy. They're certainly not, but they just are human nature trends that we have to be careful to avoid, okay? So I think if we acknowledge the safety benefits of the HEGR in the process, that helps. I think, as I said, I think in the current framework, the way it's being laid out, and based on the current work that's being done with NRC, I think, you know, we can get a reactor licensed. But nonetheless, the more credit we give for the true fundamental safety characteristics of the system, I think the more likely it will be that we'll actually be able to get to the point where we're building commercial plants like that, okay? And just to reiterate, you know, these, again, are the benefits. This is why we need to do this. And the safety profile is an important part of this because it's what allows us to get into the process heat markets that otherwise we really couldn't get into, I think. Okay? And if we don't begin soon, you know, there's a lot of talk of wanting to be able to commercialize in 2030. Well, despite the comments of people who are, you know, have less mature, well, anyway, there seems to be an inverse correlation between how mature a technology is and how soon it can come to market, you know, it is what I see. And the fundamental fact is, even with where the technology is relatively mature, like the HEGR, we have to start working pretty soon, aggressively, not just dabbling in, you know, a little bit of design work here, a little bit of R&D there, but full bore, start formal design very soon if we want to be able to start deploying commercial plants in the 2030s. So those are my comments. Anyway, thanks for your time.
Lou, I appreciate the dialogue. One thing I maybe didn't mention this morning is NRC is pretty aggressively pursuing performance-based processes and requirements, and I think it gets at a lot of your issue. I mean, you know, the proof is in the pudding, but they're working pretty hard.
Yeah.
The question I had is kind of the same one I had this morning. Maybe I'll ask it in a little different way. Is when you say that the licensing risk is unacceptably high to be able to move forward, do you have a sense for what kinds of things need to be resolved before it's acceptably high?
Well, as I said, I'm a little bit of a dissenter. I don't think I would say that it's unacceptable. I don't think there's a specific threshold at which it goes from unacceptable to acceptable. But the risk is significant, okay? And as has been said many times, we can't but before we can justify spending, using, I think, was it your numbers where you had 800 million for final design? Before we can justify spending $800 million to get the final design done, before I finally happen to get in the mail a piece of paper from the NRC that says I'm good to go build my reactor, I have to have pretty high confidence that what I'm proposing is doable and that they're going to bless it. And as I said a minute ago, if I get to the point where I've spent $700 million on design and NRC comes back to me and says, oh, you need to change this detail, and that detail is, you know, anything significant at all, then that's going to set me back in my process because of all the way everything is related. You know, it's going to cost me another $200 million. So I have to be very confident that I'm not going to get myself into that situation. And part of that confidence comes from knowing that the regulator is going to be reasonable. Part of that confidence comes from knowing myself how much margin I have in my design and how much flexibility I have in my design. So it's not a simple answer, I think. But I mean, I think, you know, on the one hand, I appreciate the industry efforts to address that question with NRC and how to get some early design phase assurance that you're on the right track. Having said that, I do think at the end of the day, one part of the current uncertainty that we face is the fact that until they actually have a design they can see in front of them, I think they're going to be very reluctant to give you much. You know.
My clarification there is there never will be perfect certainty or confidence.
Right.
So each developer and his or her investors have to make some judgments there. I'm just trying to make sure that we're working on the right things in this critical window we have here in the next 3 to 5 years while we've got the stars aligned with NRC to get everybody to an acceptable level of risk.
And I think
so that's really the reason.
And not to don't forget what you wanted to say, Finis, but just to react to that, I think a key thing is if there's going to be a process set up where as a vendor I make an initial submittal to the NRC and I get some initial feedback from them, that process needs to be structured in a way that feedback is meaningful. Okay. In other words, I don't just want something where they look at it and they say, well, looks okay so far. You know, I mean, can't really take that to the bank. I have to know that I'm clearly on the right track in these areas. These are areas I need to be careful because they're nervous about them. These are areas that aren't going to fly. I need to know that.
I'll answer more simply from my view is